In this video, we look at the characteristics of functions. Some of these will be familiar to you, some of them will be brand new, but we'll start from the beginning and we'll just kind of work our way through. So it is a bit of a long video, and I do apologize for that. So let's start with the definition of a function. First of all, a function is a relationship typically defined by an equation where for every x value, there can be at most one y value. So what does that mean? Well, that means that definition basically is the definition of the vertical line test. So this idea here that it has to pass the vertical line test. We'll do an example so you can see what that looks like. And I should also mention that we can show a function in a table, a graph, or an equation, and sometimes we use what's called a mapping diagram, which is similar to a table. So let's start with an example. We'll call this example number 1. See if we can squish a couple of examples in here. Let's look at the function f of x equals x cubed plus 2x squared plus x plus 1. Now we haven't looked at these types of functions yet, but this is an equation that defines a function. We could graph that function, and we could do that a number of ways. Later on in the course you'll know how to do it fairly easily, but we could use some graphing technology to graph that, or we can make a table of values, and when we graph it we'll get something that looks sort of like this. Kind of rough sketch here. Again, so here's the equation that we can define the function as. We can also use a graph to define that function, and we might also use like a mapping diagram or a table of values. So let's start with the table of values. Table of values would look like this. So if you didn't know how to graph this, you could always make a table of values. The trouble is you might have a hard time finding where these points are exactly, but a table of values would give you a rough estimate or a rough understanding of what this looks like. So you can choose some values, find the y values, plug the x into the equation, and find the corresponding y values. And sometimes you might see this as a mapping diagram. So the mapping diagram might go something like this. The x values listed here, and then the y values listed over here, and then you would see where the x values go, to which y values the x values go. So you might have, for instance, a function that has something like this. Now some people get confused here with that vertical line test and think that this idea of having these two arrows point to the same y value can't happen. But it's actually possible here. This says that when x is 1, y is 10, and this says that when x is 3, y is also 10. So this is basically two y values that are the same. What you can't have happen is you can't have, for a function, you cannot have two x values going to different y values. Otherwise it's just a relation and not a function. And we talked earlier a little bit about the vertical line test. The vertical line test basically says that if we draw, sorry, that's not a very good vertical line, but if we draw a vertical line anywhere on this function, the graph should cross that vertical line at most one time. Alright, let's look at an example here that of a relation that is not a function. So we'll call this example 2. And I am going to use, let's look at this. Y squared is equal to x. Now I wanted to do this on purpose. It's a bit awkward. It probably helps here to solve this equation for y. If we're going to graph this, it helps to solve for y. So when we do that, we will want to take the square root of both sides. But don't forget, when we take the square root of a number, there are two answers, a positive 1 and a negative 1. So for example, the square root of 4 is plus or minus 2. Now if we were to graph this function, sorry, this relation I should say, and again you can make a table of values here. So if x is 4, y has to be plus or minus the square root of 4, which is plus or minus 2. So if we were to graph this relation, what we would see is we would get something that looks kind of like this. It would look like this. And hopefully that's not a surprise to you. That's just the inverse function of the parabola. The parabola would be kind of this function rotated 90 degrees or reflected as well in a couple of different ways. So you can see here the point that I'm trying to make here is that this function does not pass the vertical line test because there are two y values for many of the x values. It fails the vertical line test, so this in fact is not a function. And I think you can see here that I've kind of answered this question here. Any relationship with a y squared in it cannot be a function. Why not? Well, you can see here that anytime we have a y squared, we're going to have to take the square root, and that will give us two possible answers. So it kind of jumped the gun there a little bit. All right, let's move on to the next characteristic. Just a reminder, the domain of a function is all of the possible values that make up the function, all of the possible x values, pardon me, that make up the function. So for example, if we had a function that looked like this function here, say, let's see, we'll go something like this. We'll use the square root function since we were kind of talking about it. So this would be y equals root x. And just a reminder, the x values are on the horizontal axis, the y values are on the vertical axis, and the domain here is a list of all of the possible values. Well, we don't list those off one by one because this function goes on forever as indicated by the arrow here, so we need a shortcut to do this. So here we say that for the domain, I'll just use a capital D for domain. We could write it all out, but we'll just save a little bit of time. We put it in these little curly braces, and we say that x is an element of the real numbers such that x has to be greater than, we'll make up a value here. Let's say that this is 10, just to keep this nice and simple, such that x has to be greater than or equal to 10. So that's how we would express the domain of the function listed over here. So I guess technically this is the root of x minus 10. And we'll talk more about transformations a little bit later on and see what that looks like. So that's the domain. It gives all the values. So this little funny looking e here, just a reminder, that means an element of. The r means the real numbers, so the real number systems. If I had just drawn little dots here showing what the y value is for all of the integer values, so at 10, when x is 10, when x is 11, when x is 12, and not drawn the nice smooth line that connects those dots, then I might say that the x is an element of the integers instead. But in this case, this is the real numbers, meaning that we can choose any value between 10 and 11 and get a value. And again, some notation here. We say that this is such that x is greater than or equal to 10. We should probably get that in there as well. So this part right here just means that x is greater than or equal to 10. And you might be wondering, well, what happens if the function is something like a parabola where all of the x values are included? So let's say a parabola. The parabola looks sort of like this, with arrows indicating that it goes on forever in both directions. In that case, we would say that the domain is that x is an element of the real numbers. There are no restrictions on it, and that's all we need to say, is that x is an element of the real numbers. And then the domain is basically the same sort of thing. It's a list of all possible y values that a function can take on. So again, if we look at that parabola that we just drew up here, in this case, we would say the range, and again, I'll just use capital R to indicate the range. We say that y is an element of the real numbers such that, in fact, there is no such that, oh yeah, sorry, for the parabola for y equals x squared, y has to be greater than or equal to 0. And that's how we would express the range. Again, hopefully most of this is review for you so far, and we'll start getting into some of the more challenging stuff. X-intercepts. The x-intercepts of a function are where it crosses the x-axis. So if I were to draw a graph, and again, I'll stick with the parabola. I know you're very familiar with it. If we were to draw a parabola, there would be x-intercepts right here and right here. Sometimes they're called roots or zeros of a function, put in the bracket here. Sometimes they're called roots or zeros solutions sometimes as well to equations, and we'll kind of get to that a little bit later on, and you've seen some of that already. And the way that we find these x-intercepts, that's an important idea, is that we set y equal to 0 and solve for x. So that's an important idea. Set y equal to 0 and solve for x. The y-intercept similarly is where the function crosses the y-axis. So, for example, why don't we use a straight line on this one? I know it's hard to draw a straight line without a ruler, but in this case here, the y-intercept where the graph crosses the y-axis would be right here, which you're very comfortable finding using a linear model. But if the equation is not linear, again, the same sort of thing here. We can just set x equal to 0, set x equal to 0, and solve for y. All right, so that's some more review. Again, we'll get into some more terminology that you're comfortable with. Maximum and minimum values. In the past, you've looked at these, especially dealing with parabolas or quadratic functions. You can see that this function has a minimum value right here. The function is never less than -2, as indicated here on the y-axis. We're going to talk about an absolute maximum or minimum. So again, the lowest or highest point reached by the function. And you can see that here because we're going to get into some functions that look like this one down here that have multiple maximum and minimum values. And you might be looking at this graph saying, well, this is the minimum of this graph. It's the lowest possible point. And that's what makes this an absolute minimum. This point right here is an absolute minimum. The function never goes lower than that. But this is like a minimum as well, and we call this a local maximum. A local minimum, because it hits a minimum value here. So this is a local min here. And similarly, we have a local maximum here. Now you might look at this and say, well, that's the largest kind of bump on the graph. Isn't that the largest possible value? But don't forget, this graph actually goes off forever in both directions here, getting infinitely larger as we kind of head off this way and this way. So this is a maximum, but it's only a local maximum. So an important distinction there between local max and min values and absolute max and min values. All right, you've looked at asymptotes before. We're going to expand that a little bit in this course and look at some other things that happen as well. So basically, just a reminder, an asymptote is are lines that functions get infinitely close to and don't touch. You may have heard in the past the terminology saying that the line gets close to but never crosses. I'm going to try to steer you away from that because we will look at asymptotes that do get crossed, and we'll talk a little bit more about that later. But what we want to do right now is look at lines that the function get infinitely close to but don't reach. So for example, you can see here the y-axis, I'll try to highlight it in green here. The y-axis is an asymptote. This function is getting infinitely close to it, both up here and down here, but never actually reaching it. So that would be an asymptote at x equals 0 would be a vertical asymptote. So I'll just use the letters VA for vertical asymptote, and we would say that we have a vertical asymptote at x equals 0. We also have a horizontal asymptote in this graph. So again, if I draw a line going across here horizontally, you can see, let's try that, finish that properly. You can see that the graph is getting infinitely close here and here, but it's not actually reaching that point. So that's important to realize as well. And as I said earlier, I want to steer you away from that definition of a function not being able to cross an asymptote. And the reason for that is that it is possible for a function to cross a horizontal asymptote. And we'll look at that a little bit more when we talk about rational functions. All right, let's talk a little bit about what's called end behavior. This is a little bit of a tricky concept. The end behavior of a function basically deals with what's happening at the end of the graph. So if I can go back here and just erase my scribbles here so we can see the graph. And when I say the ends of the graph, what I really mean is what's happening out at infinity. What's happening way out here. So what we want to do is we want to try to describe what happens to the y values as x gets infinitely large in both the positive and the negative direction. So the way that we do that is we say that as x approaches, and again we'll shorten this up, so instead of writing the word approaches, we'll just draw an arrow. As x goes towards positive infinity, what's y doing? Well, you can see that the y value is getting closer and closer to this horizontal line, or in this case the y-axis. It looks like as x approaches infinity, y is approaching 0. So that's a way to describe the end behavior, but that's only in the positive direction. Let's look at the negative direction as well. So as x approaches negative infinity, what's happening to the y values? Well, again, as we get closer and closer to negative infinity, so further and further out, this function is going to get closer and closer to that x-axis, pardon me, but never actually reaches. So we say that y is also getting closer and closer to 0. So that's for that example. Let's look at another function that you might that you should be familiar with, and that is the quadratic function y equals x squared, again, just to see comparison between the end behavior. So in this case, again, we want to look at the end behavior. So we want to look at what happens as x goes towards positive infinity and what happens as x goes towards negative infinity. I'll give you a second to have a look and see what you think. Well, here's our x value going towards positive infinity in this direction. Well, what's happening to the y values? The further out we go this way, what's happening to our y values? Well, they're just getting bigger and bigger and bigger. So as x goes towards positive infinity, we say that y is going towards positive infinity as well. So y goes towards infinity. And again, you really have to look at each graph on a case-by-case basis and just look at what's happening. So what's happening here as x goes towards negative infinity? So as x goes towards negative infinity, the y values are getting infinitely large. So y is going towards positive infinity as well. So that's what we mean by the end behavior. All right, positive and negative intervals. This one trips students up sometimes, so we're going to spend a little bit of time on it, hopefully making sure we get it right so that you know what's going on. Basically, what positive and negative intervals are is it's where the y values are positive. So describe using the x values where the y values are positive. So I'm going to use this graph here again that we've used a few times here. So let's start by looking at where are the y values positive. I'm just going to circle those in green for now. So the y values are positive right here. They're all above the x-axis here, all the way over to here. All of these y values are positive, but the y values are also positive over here. So when we want to describe these intervals, we use the x values to say where they're positive. So the x value where they were positive basically started here and ended here. So let's go here and write in the positive intervals. Whoops, that's supposed to be an I. So the positive intervals, basically between -3 and 1. So -3 all the way to, so these are x values. So x from -3, let me start that over again. I kind of squished that in there. So when we're talking about positive intervals, we are looking at the x values and we're saying from -3 all the way to +1. Now, this is an awkward way to write this. I suppose we could write it like this, saying -3 is less than x, which is less than 1. So that describes the interval, you know, with x in between -3 and 1. Now, there is another type of notation called interval notation that you should be familiar with or become familiar with. Now, interval notation is a little bit weird. It's weird in that it looks like it's an ordered pair. So if I were to write this interval, this as an interval, I write it like it's an ordered pair, saying we're going to start at -3 and we're going to finish at 1. So the part that's confusing is that this looks like an ordered pair, but both of these are x values. So I'm going to write that down. These are x values. and this is the start of those x values, and this is the end of those x values. So this is interval notation. You should get comfortable with both types of notation. So we had the one interval that was positive. We also had the other interval from 2 onwards. That was this part in the graph over here. Oh, I should have changed my pen color to green maybe. But from 2 onwards here, let's try that again. So that was this part over here. So basically, if we were to write that, you might write that before as from 2 less than x, which is less than infinity. But in interval notation, let me just slide this out of the way actually. You know what we're going to do? We'll just move that right up over here, just so that I can keep the interval notations together. If you've taken data management and you've talked about sets, you would know that work about sets. We use this capital U to represent the union, so it's this set or this set right here, and we are going from 2 all the way to infinity. So those are the positive intervals. The negative intervals basically is just, sorry, that's supposed to be an I. Negative intervals, where is this graph negative? Well, this graph is negative anywhere it dips below the x-axis, basically from 1 to 2. And I'll just do this one in interval notation because I am running out of space. Basically from x equals 1 all the way to x equals 2. Up to, but not including those points. So the interval notation, I'll just make a special note down here. I know I kind of did it here. This is like your x start and your x finish. So where does the interval start and where does it finish? So this is an interval of x values. And we'll use this interval notation in a couple of other places as well. Sorry, this is interval of x values. All right, let's move on. So here's another place we're going to use it. We're going to talk about the intervals of increase and decrease. So essentially, same idea. It's a description of where, so talking about the x values, where are the function values or the y values increasing and where are they decreasing? So you can think about this a couple ways. You can look at just where are the y values getting bigger as you move from left to right, or some people like a little visual. So I imagine you're standing here on the x-axis, and as you move from the left of the page to the right of the page, what's happening to the y values? So you can see down here the y values are really small, but they're getting kind of bigger. So they're growing. They're certainly growing here. They're getting bigger. They're getting bigger as I walk from left to right. They're getting bigger. And then we get this far, and we can see that the y values are starting to decrease. So the interval of increase basically is along here. The function is certainly increasing along here. And then we can see the y values as we move along here. The y values are going down, they're going down, they're going down, and they stop right here. So this interval, let's say from here to here, we're decreasing, and I'll just write that in here. Over here we were increasing, and then afterwards, again, we're walking along the x-axis. We can see that the y values are getting bigger as we move this way. So this is like an interval of increase over here. So again, we can use that set notation. So the interval of increase is all the way from negative infinity, like way out here. The function, you start your walking all the way somewhere out here, and you walk from left to right. These values are getting bigger and bigger. So this interval starts at negative infinity, and it goes all the way to this point right here, which looks like, and I'm going to just eyeball this from the graph for now. We'll talk later about how to find it exactly, but it looks like negative 1.5 or negative 3/2. So we'll say negative 1.5 for now. So that's an interval of increase. We do have another interval of increase out here. So we're going to put that little u for the union of the two sets, and this set starts at 2 and goes all the way to positive infinity. And then we can look at an interval of decrease. Where is this function decreasing? Well, it's decreasing, we'd said already, from here. And again, we'll kind of eyeball this and say that this is from negative 1.5 to 1.5. So the x value where the interval starts decreasing is negative 1.5. and it goes all the way to positive 1.5. So those are the intervals of increase and decrease. All right, let's talk a little bit about, this might seem a little bit odd to you, but we're going to talk about holes and jumps. So holes are sometimes called point discontinuities. Basically, they are gaps in the function causing it to be discontinuous. So remember, a function is continuous. I'll show you a continuous one first. A function is continuous if we can draw the whole thing without lifting our pen. So there's an example of a continuous function. So what happens with holes is that you get essentially a graph, and in fact I'll use the exact same graph, where you just get this little hole. I mean, it's called a hole because there's literally a hole. So there is no value in here. This function has no y value here. So if this is at x equals 2 and say y equals 4, the function is continuous. I can draw this, and then I have to lift my pencil up to keep going. Now we do show it with a little open circle, just because if I were to draw a function like this, and if I were to lift my pen up here and put it back down, you might not see that little gap, and depending on the size of the gap. So we draw a little circle around it to indicate that there is in fact a little hole there. So that's what we call a hole in the graph. You might wonder, how do you get a hole like that? We'll talk a little bit more in a few weeks about what that looks like and how you get that value. A jump, on the other hand, is the same idea. It is a discontinuity in the graph, but it looks very different. So the y values actually jump from one to another. So here there was a clear, like, there's a gap here. The y value was supposed to be in here, but it's not. With a jump, you get something that looks more like this graph here, for instance. Let me try to draw that again. Sorry, that's a terrible set of axes. We'll try to get something a little straighter. Ideally, I should make a set and just copy and paste them. But all right, maybe that's not much better. But all right, so here is our function. Our function is going to look like this. And we're going to say that the origin is included on this part. So I'm just going to draw a big circle here. Try to exaggerate it. Obviously, it doesn't need to be that exaggerated. And then, again, on the y-axis, the rest of the function looks like this. So this is what we call a jump, because there was a jump in the y value. And this happens when a function is basically defined as two separate functions. So this function might say the function f at x might equal, let's say, y equals x for this part right here, if this is the line y equals x. So f at x equals x, or 2 to the x. And this was for, so y equals x on the interval, sorry, let me just draw my little, for x less than 0. I should have drawn this a little bit bigger. And this is for x greater than 0. So what this means is that this function is defined as this if x is less than 0, and as this if x is greater than 0. So we get this discontinuity here. Again, I can't draw this without lifting up my pencil. I have to lift up my pencil to draw this graph, and that's how we get this point discontinuity. And I should mention here, I was a little bit sloppy in my notation. This should have said that x is less than or equal to 0. If x is equal to 0, the filled in dot is this part right here. The filled in dot indicates that what happens when x is equal to 0. Well, this is included in that part of the graph. All right, and the last thing we're going to talk about here are turning points. You've seen these before. We haven't called them turning points, but basically the graph, a turning point happens where the graph changes from increasing to decreasing, or vice versa. I should say that here, or vice versa. So, for example, let's draw a graph. We'll draw a nice big one. Let's draw this one right here. So where does a turning point happen? Well, the turning points happen where the graph goes from increasing to decreasing. So you can see that the graph is increasing here. The y values are getting bigger and bigger and bigger. And then boom, right here, they stop getting bigger and they start getting smaller. This is a turning point. And there's another one here because the graph is decreasing, 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 and then it starts increasing. So another turning point down here, and we have another one here and another one down here. So some of you might be wondering, is a turning point just a maximum or a minimum, local maximum or minimum, or even an absolute max or min? Yes, all max and mins are by definition turning points, but there are other things that are turning points as well, which you will talk about a little bit more when you get to the calculus course if you are going that route. All right, so that was a very long sort of lesson on characteristics of functions. We will be using these throughout the course, so it's good to kind of get some practice and get familiar with the stuff that you don't know and refamiliarize yourself with the stuff that you know.